Hey there, 205. Today we are going to talk about multiple linear regression. But just as a reminder, these are the sections that we have been going through in this unit. So we're on the last part of this unit, interpreting a linear regression with controls, also known as a multiple regression. So in the last few videos, we were looking at something called a bivariate regression, where we just looked at how much one X variable or your independent variable affects your dependent variable Y. But you might be thinking, what about all of those control variables, which are additional predictor variables that we talked about earlier for observational studies, right? If we're not running an experiment, we have to control for stuff. When do those come in? Don't we want to make sure that it's not some alternative factor that's actually affecting the dependent variable? When does that come in? That comes in now. So let's check out what we were doing previously in the other videos. We were looking to see if age affects how much people like Donald Trump, same exact numbers that we saw before. And it looks like, if you look at the p-value, age has a statistically significant relationship with that Donald Trump feeling thermometer. But let's go think about these alternative explanations. We've done this before, right? Aren't older people just more likely to be Republican, for example? That's a relationship that we know exists. So couldn't the data for someone's age, all of these people filling out their age in a survey, couldn't that data just also be capturing someone's partisanship? Since those two things correlate, look at me, these two variables correlate with one another. If that's the case, maybe it's actually partisanship that's affecting how much people like Trump rather than their age. So here's what we have to do. These two look at me, these two variables correlate, they're wrapped up in one another. We have to separate the effects that they have on the feeling thermometer from each other, right? They are correlated, they're wrapped up in one another. We have to separate them from each other to see if they have their own relationship with how people feel about Donald Trump that are unique from one another. That's the logic of what we're about to do here. That's where multiple linear regression comes in. What this does is it estimates the effect of many predictor variables uniquely from one another. So they're all going to have their own effect that's independent of every other variable in the model, okay? So we are adding control variables, which are predictors, as we already said, and we are going to examine whether our main independent variable, the thing that our hypothesis is about, does that remain statistically significant? So does that still have a significant effect on the dependent variable, even when these controls are added? Or in other words, even when these alternative explanations are accounted for? That's what we're doing. So this is the original bivariate regression. This is what it looked like. So let's add partisanship as a control variable. We're just going to start by adding one thing. So if we were to add party ID, so over here in the new regression, which has one control, now we have a new row for party ID. Let's talk about what has changed in this regression once we added that in. So down here it says, first of all, the constant changes. So the constant on the left was 30.00. Now the constant is negative 7.23. So once in a while, you don't have to think that hard about this, but once in a while, the number that we get for the constant doesn't make much sense. Our dependent variable ranges from 0 to 100, which means the constant has to be between 0 and 100. This went to a negative number. Sometimes it does wonky stuff like that. don't think about it too much. Just know that the constant can change when you add new control variables in. So that's a strange one, but whatever. Number two, this is what's actually more important. The coefficient for age has also changed. On the left-hand side, it's 0.242. Suddenly, when we add partisanship, that number has gone down to 0.162. That actually makes sense. We would expect that partisanship, because it's correlated with age, is actually doing some of the work here. It's actually affecting the dependent variable to a pretty high degree. So it has shrunken the effect of age. Age now matters less because partisanship is being included. So that has changed. The p-value, however, for age has remained highly significant. It's still 0.000. So even when age is thrown into the model, even when partisanship is thrown into the model, age is still significant. Sometimes, and actually a lot of the time, when you add control variables, suddenly the p-value for your main independent variable just, up and goes away. Like it'll go up to, 0.24 or 0.59, and suddenly it's not statistically significant anymore. If that happens, that means it really wasn't your main independent variable affecting the dependent variable. It was something that correlates with it. So we're trying to see, does that p-value stay statistically significant even when we add a control? And right now it has stayed statistically significant. You will also notice that the R-squared value has jumped substantially. Over here on the left, it was 0.01. Age was explaining about 1.5% of the reasons for why people like or dislike Donald Trump. When we add partisanship to the mix, suddenly those two variables combined, age and party ID, they're explaining 0.453. So in other words, 45% of the reasons for why some people like or dislike Donald Trump. That's an enormous jump. And it's one that we would expect. Partisanship explains a lot about why people like or dislike this person. So those are things to take note of. But let's just focus on that one in red with the age and the party ID. Let's interpret it. So when you interpret this, the way that you interpret the numbers is exactly the same as a bivariate regression. Nothing has changed there. But now we can make stronger claims, right? Now we can say, if an effect pops up that's significant, it's independent of the other controls that are in the model. So let's do age. Age is measured in years. We're going to do it the same way that we did last time, right? So for every year that people get older on average, the feeling thermometer goes up by 0.162 degrees. So 0.162 degrees going to 19, 0.162 degrees going to 20, and so on and so forth. As people get older, they like Donald Trump more. But now, here's what we can say. As age goes up by 1 year, the Trump feeling thermometer goes up by 0.162 degrees. As people get older, they like Trump more. Here's the important part. This effect is unique from partisanship, and it's statistically significant. So if someone came along and said, it's not age that's causing people to like Donald Trump, it's partisanship, you can say, no, I pulled those two things apart from one another, and there still seems to be something special about age, even when partisanship is included. So this is separate from partisanship. Let's do the same thing with the partisanship variable. Party ID, as you can see in the code book, is on a 7-point scale that goes from a strong Democrat to a strong Republican. So a unit increase means people are getting closer to strong Republican. And the coefficient is 10.75, and the p-value is 0.000. So we would say that as people move 1 unit towards becoming a stronger Republican on the scale, so going from 1 to 2, that thermometer goes up 10.75 degrees. And then going from 2 to 3, it goes up another 10.75 degrees. So if we were to go all the way from a strong Democrat to a strong Republican, that is a very, very big difference in how people rate Donald Trump on that scale when you add up all of those degrees. That makes sense. So now here's what we can say. As people become stronger Republicans, they like Trump more, and this effect is unique from age. If someone said it's not that people are, more Republican, it's just that they're older, you can say, no, those two things are separated now. They're unique from one another. This relationship is highly significant. P is less than 0.001. So these two variables are estimated uniquely from each other. So that's how you would do this interpretation. The numbers are the same. It's just that you can make stronger claims if you're finding statistical significance. So let's see what it would look like if we put in a lot of controls. So we talked about how many control variables people usually put in. It's usually between 5, 6, 7, or 8. Let's say, and you want to choose variables that make sense, right? These are the variables that are most likely to predict your dependent variable. So let's say we're going to see, does age still hold up even when we talk about all of these other variables that might affect how much people like Donald Trump? And every single one that you see here is estimated uniquely from all the other ones in the model. So for example, age, our main independent variable that we've hypothesized about, it's a small coefficient, it's still significant. It's still significant at P is less than 0.01. And this effect is independent of, let's go down the list, partisanship, ideology, religiosity, people's opinions on whether immigrants harm US culture, their opinion on defense spending, their race, whether they have a college degree, whether they think politicians are trustworthy. It's separating age from all of those things that it might correlate with. Likewise, if you look at the effect of partisanship, which is big and it's still very significant, that effect is unique from age, ideology, religiosity, whether or not people think immigrants harm the culture, defense spending opinion, their race, whether they have a college degree, whether politicians are trustworthy, and so on and so forth. All of these things are estimated uniquely from one another. So these are powerful statements that we can make if we are finding statistical significance with the p-value.